Welcome back to Meaning from Data, Statistics Made Clear. Data. Data. Statistics starts with data. Governments, businesses, universities, sports fans, they amass mounds of data about people, about products, academics, win-loss records. You talk about the age of people, salary, gender, position, price, measurements, graduation rates. World records, they're all assembled into massive tables. Our question is, how can we understand this ocean of numbers? And that's the role of statistics. So lectures 2 and 3 together give a global introduction to the whole course. And in this lecture, lecture 2, we're going to introduce the concepts that are used to understand a set of data when we know all the data about the population that we're interested in. For example, if we know all of the incomes of every employee in an organization. In lecture 3, we'll go on to discuss how to infer information about the whole population when all we know is the data about some people in the population, some members in the population. An example is, how can we, the most common example is, how do we infer the opinions of the whole population of voters when we just take a poll and ask a few people how they're going to vote? So, and then lectures 4 to 7 will describe what we do today in more detail, how to analyze a set of data when we know all the data. And then lectures 8 through 12 do the same thing for statistical inference, looking at that in more detail. Okay, so we'll begin. The world is full of tables of data. And in this lecture then, we're going to try to come to grips with how to make sense of such lists by illustrating these techniques that we'll develop by looking at several examples. Always, the challenge is to organize, describe, and summarize a set of data. Well, frequently, the best way to get this meaning from data is to draw a picture, to make a graphical representation that really brings home the message. And to illustrate this, that there are many different ways to graphically illustrate a set of data. And one of the imaginative ways to do so was actually invented by Florence Nightingale. And in 1857, she wrote an article called, a paper called Mortality of the British Army, in which she was displaying how it is that the rate at which soldiers were dying in the Crimean War. She had a method of displaying these, which are called the Nightingale roses. And you can see here in your picture 2 examples of these Nightingale roses. They're interesting because they are sort of like the familiar pie chart that you've all seen in newspapers, where you take just a circle and have sectors where the size of each sector illustrates how many things there are in that sector. But this is a little different. Here she has, in this illustration, 12 equal angled pieces of a circle. And then what she does, and one for each month. Notice that one is for each month. I don't know if you can read that, but on each one of these sectors is a month name. And then the size, the area of that sector, it goes out, the bigger ones indicate that there were more deaths during that month. So the point is that by looking at this diagram, you can see the months in which there were a lot of deaths. Now down near the bottom, January, see December, January, February, March. And then comparing this diagram to the other diagram, you can easily compare the different rates of death because the months occupy the same sector. So that if you have big pieces down on the left on one side and short on the other one, then that's a way to compare the 2 things. So this is an example of a very interesting graphical representation of data that's rather imaginative and can make a point in a graphical way come out at you. And she actually used this to try to argue for changes in the way that the hospital and medical treatment of soldiers were done. In fact, from her data, she showed that the enemy of the actual physical enemy for the soldiers was the least of their worries. They were dying more from their treatment and hospitalization than they were from enemy fire. So looking at data graphically is one of the primary ways to understand data, and we'll see many examples during this lecture. Let's go on to an example here, which is a list of salaries for a particular group of professors. Now, I was an associate dean in the administration at the University of Texas for some time, and so I can assure you that every professor, according to him or herself, is underpaid. You see, underappreciated, and of course that's all true. And one thing that a professor will do in order to bolster the case is to bring in data showing how it is that his or her salary is low relative to the other people who should be compared to. And so one of the kinds of things that person would do is to bring in a list of all the data. So suppose that this professor brought in this list of data that showed all the salaries of comparable people. And in this list, this is just one page of many pages of about 630 comparable salary data that this person has amassed. And notice, first of all, that if this person brought the data in this way, it's meaningless because there's no structure to it. It's just a lot of numbers. There'd be no way to look at that and say, oh, yes, well, you're right. You're way underpaid. So what we need to do is to organize the data. And the first and simple way to organize it is to put it in order. Put the data from the lowest salary up to the highest salary. And so this list of data does that. As you see it on the screen now, it's the first few numbers in this larger list of data. But once again, this list of data doesn't really do much in the way of conveying information, although we now can look at this data in this form and at least say that the highest paid person had in this category was $105,550, and the lowest paid member was earning $52,290. So that at least is something that gives us some brackets. Well, it's common to take a collection of data and to summarize it into one number. That's probably the most common way to summarize data. And a good way to summarize it would be to take the mean of the data. So, for example, we could add up all of those numbers, the 630 numbers, divide by 630 to get an average value, and that value is called the mean. The mean is the number obtained by adding up all the numbers and dividing by the number that you have. In this case, $68,500 is the mean of those data. But the mean may or may not be a good summary of the data because maybe there are a few very wealthy people, or that is people who are making a very high salary, that make the average higher, that is the mean, higher than a representative value. So a different kind of a summary number may be more valuable. In this case, you might want to look at the median value. The median is the middle number on the list. If you order all the numbers of a list from the lowest to the highest, and then you take the middle one and see what that value is, that's called the median. So the definition of the median is the middle number. In this case, there are about, as I said, 630 data items, so the middle one is the 315th, and its value in this case is $65,600. So the median is a center value, and it just like the mean is a different concept of center. It's a measure of the center. Well, we can see that we could play this game a little bit in more detail by saying how many people make 25% of the people. You know, what's the amount of money that the lower 25% of people make? The value of the person who earns, putting them in order, 25% up is called the first quartile. So we have the first quartile, which is 25% of the way up. In this case, the first quartile is the 157th item, which is $63,480. So that's called the first quartile. So it's the value, again, so that 25% of the data items are less than or equal to that value. And then 75% of the data items are, of course, higher than that value. And likewise, the third quartile is the value of the number, that in this case, the 472nd number on the list, so that 75% of the people earn less than that value. And in this example, $75,350 is the amount that is exceeded by only a quarter of the people. It's more than 3/4 of the people. So one way to summarize this list of numbers is to give 5 values: a minimum, the first quartile, a median, the third quartile, and a maximum. This gives a 5-number summary for the data. And it gives some sense of the whole data set. We can summarize it in a picture form by looking here at this, what's called a box plot. The box plot just shows where the lowest edge of this box happens at the first quartile. You see it here. The horizontal line in the middle of the box occurs at the median. That's the middle value. The top of the box occurs where the third quartile is. And then it goes up here to a range above which are viewed as outliers or potential outliers. These are people who make money that somehow fits outside the range of most of the salaries. And there's a particular heuristic about this, namely you take 1.5 times the distance between the first quartile and third quartile and go above the third quartile that much, and anything above that is viewed as a potential outlier. But that's just a heuristic, and the point is that the box plot summarizes the distribution of the data, how the data are spread out. Well, the problem with this summary is that it isn't too specific. It's helpful in giving a range of data, but it's not as detailed as we might want. Another way to summarize the data is using a histogram. And a histogram is a good method for saying how many people make this much, how many make this much, how many make this much. What we do is we simply divide the incomes into groups. In this case, we've done $5,000 increments from $50,000 to $55,000, $55,000 to $60,000, and so on. And then for each one, we just make a bar that goes up as high as the number of people who earn income in that range. So this is a histogram. And so, for example, this bar right here is between $65,000 and $70,000 in our long table of numbers. We just count how many people made between $65,000 and $70,000, and we see it's about 118 people made that amount, and that's the height of the histogram. When we take all of these bars of the histogram, you notice that it has a shape to it. And that shape of the data is a good way of getting some sense of the distribution of the data. So a distribution is the fundamental idea of looking at a whole data set. The distribution of a set of data is defined as the values that this variable takes, like salaries, and how often it takes them. So the distribution is summarized and takes on a shape by looking at the shape of the histogram. Now, notice that the histogram doesn't need to be $5,000 increments. That was just a choice we made. We could have made $10,000 increments and we get a different histogram of the same data, a different kind of visual summary of the same data. Notice that if you took very small increments, for example, just $1 increments, then it may be that your histogram would give you no useful information because there maybe no two people make exactly to the dollar the same amount of money, and therefore you just have a bunch of dots on the line. So that wouldn't be a helpful summary. So choosing how big the groupings are is one of the choices that we have to make in order to make to give us a sense of the shape of the data. The next example we have is a histogram of SAT scores at a particular, for incoming students at a particular university. And once again, we can notice something about the shape of this histogram. The histogram has groupings of 40 points, increments on the horizontal axis, and then how many of the students got SAT scores in that range. So this by just going up here, for example, here getting about 1,000, between 980 and 1,020, there were about 16 students in this class who got that range of scores. Let's just look at a couple other examples. These are the heights of American male adults. And in this case, instead of measuring the number of people who are at each of these heights, by the way, are in 2-inch increments, like between 68 and 70 inches. Instead of the number of adults in our survey, this is now talking about what fraction of the male adults had that particular height. So in this case, for example, the highest bar here is between 68 and 70 inches. That's 5'8" and 5'10", and about maybe 13% of the population of adult men arrived had that particular height. So the histogram is giving us information about the shape of the data, how the data are dispersed. It's not telling us just one number summary, but it gives us a picture of how the total heights of people in this case are arrayed. So it gives you a sense of the variety, which is I'd say one of the big lessons for this whole course is don't just rely on one number. You often just hear one number in a newspaper. It'll say the average of something, the average income is such and such. But what you really want to know is how are the data dispersed? Are there a lot of people that are on one side and a lot of people on the other, or are they all concentrated in one center part? So these are giving an idea of looking at the shape of the data. So here we have the American males. You can see that the data are sort of symmetrical around a center value. This is a different graph. This graph represents an experiment undertaken in the following way. For 10 Wednesday afternoons at a toll booth on a highway, from 3 o'clock to 4:40 in the afternoon, the number of cars coming in were counted. Between 3 o'clock and 4:40, that's 100 minutes. 100 minutes. And so for each Wednesday, for these 100 minutes, you looked at every minute how many cars arrived at the toll booth during each of those 100 minutes, and did that for 10 weeks in a row, meaning that there were 1,000-minute intervals in which, for each such interval, you counted how many cars arrived during that minute. And then this is a graph that shows how many intervals had, in this case, 0 cars arrive, how many intervals had 1 car arrive, 2, 3. So for example, the height of this, about 100 of the intervals, 3 cars arrived. Do you follow that? It's a little bit tricky. For example, here, 6. This says that there were about 148 intervals, 6 cars arrived. You see, follow me? So you took this data and just counted how many intervals different numbers of cars arrived. And in this case, notice that this is a little bit skewed to the right, meaning skewed to the right means that there are more data points to the right than the left. It's not quite symmetrical around its middle line. Like the heights of men were sort of symmetrical around a point. This one is a little bit off. And it may not look too much off. It looks pretty symmetrical. Here's an example that's more unsymmetrical yet. This graph displays data about deaths by mule kicks in the Prussian army. The study involves about 10 corps of the Prussian army, each followed over a 20-year period, for a total of 200 corps years. In 109 of those corps years, happily, no soldier died from being kicked by a mule. In 65 core years, 1 soldier was killed. In 22 core years, 2 soldiers were killed. In 3 core years, 3 soldiers were killed. And in one very sad year, a single corps suffered 4 deaths from mule kicks. So this is an example. What we're trying to get at here, by the way, is some movement toward understanding that the shape of the data is something that we want to describe. Is it symmetrical around a center point? Is it pushed down toward the right? In the case of the mule kicks, it all just sort of had the big part at 0 and went down to the right. Here's an example of SAT scores at a school that is a K through 12 school, where every student who's in the 7th grade takes the SAT test, and then they take it in the 11th grade again when they're getting ready for college. Now, you can see that what happens here is that the 7th graders tend, of course, to get much lower scores. They're only in the 7th grade, for heaven's sakes. And then by the time they get to the 11th grade, they tend to have higher scores. So putting those data together, we get what's called a bimodal distribution. It has 2 separate peaks to it. Here's a histogram of the heights of females. Notice that the distribution of the heights of females is very similar to the distribution of the heights of men in the sense that it is symmetric, but it has a difference. The difference between the heights of females and the heights of males is, yes, that the heights of males were centered, remember, at 68 inches, and the heights of females are centered here at about between 62 and 64 inches. So that then illustrates an idea of the center. The difference between the graph of the males and the graph of the females is a matter of where the center of the graph is. So what we're trying to do is to develop some concepts of what we look for in describing a distribution. One thing that we look for is the shape. We talked about the different kinds of shapes: symmetrical, bimodal, skewed. Those were different categorizations of shape, and now we're looking at something that can distinguish one data set from another data set, namely where they're centered. So this is the heights of women versus heights of men differ by the place where they're centered. Now let's go through one other example that will bring up another feature of data sets, and that is the concept of how widely dispersed the data are. So this graph is a histogram of the batting averages of Major League Baseball players in the year 2000. By the way, this graph does not include people who only batted a few times. This only includes batters who batted more than 80 times, and so they have a legitimate batting average. And we'll notice how these data, they're centered somewhere between 250 and 300 batting average. But notice what happens when we compare that histogram to the histogram of the batting averages in the year 1920. Now, they look very similar. I know they look very similar, and I'll go back and forth a couple of times so that you can see the difference. But let me describe it. The center of the batting averages from 1920 was almost identical to the batting average in the year 2000. In fact, the batting average in 1920 was within 1 point. It was, in one year it was 266, the other year it was 265. So the two were within they were essentially identical batting averages over the whole population of batters. But look here, although the center is the same, the batting averages from the 1920 era are more spread out than they were from the year 2000. You see how it's taller here? This is taller, and these are taller, and they get very thin, between 300 and 350 and 150 and 200. These are very small by that time. Now look what happens in the year 1920. This is not as tall, and then these are more spread out. And by the way, they're made in comparison, they're made so that the total area of these bars is identical in the two places for comparison purposes. The total area of the bars is the same, so you can compare them. And in fact, we can overlay them And it may be a little difficult to see, but the top part here represents the batting averages from the year 2000. You see it's under here at this point. So here's the batting average from the year 2000. And it drops down. And the blue, which is the batting average from the year 1920, is more spread out. You see there, this is taller at the ends. Now, this is illustrating the difference in distributions associated with spread, how dispersed the data are. So what we've come to is 3 principles for understanding data. That is, for organizing, describing, and summarizing data. There are really 3 things to look for, and they are the shape, the center, and the spread. So shape, center, and spread are 3 characteristics to try to describe. Now, in future lectures, we're going to try to develop specific models that will help us to describe various shapes. Very specific models, in fact, mathematical models that will help us to describe shapes. And then we'll develop particular measures for how to measure how dispersed the data are, how spread out those data are, or compacted, so that we can look at the data between the 1920 batting averages and the year 2000 batting averages and give a quantitative sense of how spread out they are. But for now, we've seen that looking at the shape, the center, and the spread are characteristics that we want to develop in describing the differences between sets of data. Now, the next concept, when we have all of the data in a collection, a very fundamental aspect of getting meaning from data, is to look at the relationship between 2 varying aspects of the same individuals in the population. A good example of that is the SAT scores, that is the score on this scholastic aptitude test, versus how well the student did, the grade point average the student got in college. Those are 2 characteristics of the same student. How can we compare the 2? Well, one way to do it is to draw a picture of comparing them in the following way. For every student, we have 2 pieces of information about that student. We have what that student's SAT score is and what that student's grade point average was after the first year. So this is students who have already had more than 1 year of college. So in this, if we look at every single dot, every dot corresponds to 1 student. For example, this dot here had an incoming SAT score of, let's see, this is 1,000, this looks like about 1,020, and didn't do too well, grade point average less than a 1, right? And so, and this student here had an incoming SAT of about 1,200 and had a grade point average of maybe 1.9. So you follow me, every student is represented by a dot. And this scatter gives you a sense of the extent to which a change in the SAT score is correlated with a change in the grade point average. And in fact, we can summarize that in a helpful way by drawing a straight line that tries to capture the sense in the extent to which the direction that those 2 things are going. You see, it's going up to the right. It's true that higher SATs do seem to produce somewhat higher grade point averages, but on the other hand, it's sort of all dispersed about that. It's not right close to a real close line. It's not saying that, boy, your SAT score is really determining your entire future at college. That's not true at all, you can see, and yet there's a general correlation. So in summary, the basic way to get meaning from data, when we have all the data of a population of interest, involves the concept of the distribution. And the main aspects of a distribution that we look at are its shape, its center, and its spread. Histograms and box plots are useful graphical aids, and quantities such as the mean, the median, and quartiles are often used to measure or summarize the data, but they don't preserve all of the information. And data come in different shapes, and some that we'll run into often and can describe mathematically. When we have associated data, we can visualize them by graphing a scatter plot. And we can sometimes approximate the relationship between these related data by a straight line. All of the concepts, by the way, in this lecture will be quantified in future lectures. So this lecture's purpose was to give mostly a qualitative view of methods of organizing, describing, and summarizing a set of data. Perhaps the first three rules of statistics should be draw a picture, draw a picture, draw a picture. A visual representation of the data gives us the patterns, shows us the relationships in the data. A graph can show us the important features of the data, such as its center, its spread. It can show unexpected values, such as outliers. An image can be used to tell others the story that the data contain. Typically, we describe distributions of data by characterizing the general shape of the distribution, finding where the distribution is centered, and then measuring how spread out or how concentrated the data are from that center value. In the next lecture, we'll introduce the concepts concerning statistical inference, where we infer these features of a data set when we just know values, when we just know the information about some of the members of the population. See you then.